Hopefully those were pretty easy. Can somebody tell me something nice about each one of these? Or tell me something that's missing from some of the ones that we did before.
No fractions.
No fractions. Okay, so hopefully this is pretty easy. Let's see, vertex here. I'm going to blow this up so we can take a good look at it. Says just graph and then state how many x-intercepts it has. So really all we need here is, let's see, the vertex is at 2, -9, opens up, vertically stretched, so we go to 2 and -9, so we're all the way down here. If I were to graph a couple of points, so I'd go over 1 and up 2. If I go over 2, I'd go up 8, so that's going to put me about right here and about right here. So the graph's going to look something like this. Come down here. It does look vertically stretched. Okay, all it says here is graph it. That's a decent sketch of the graph. We could label the axis of symmetry and all that. This is, of course, x equals 2 because it's a vertical line, so it's x equals a number. But it says, how many x-intercepts does it have? It has 2. 2 x-intercepts. Because an x-intercept is where the graph crosses, whoops, thinking ahead there, crosses the x-axis. So let's take a look at the next one. The next one, the only thing that's been done to this is left 3. And why did it move it to the left 3? Why is the vertex at -3, 0? Starts the graph 3 units sooner. It makes the -3 act as if it were a 0. So it comes down here, goes like that. And we could label a couple points on here if we want. This is just the plain old parent graph shape. How many x-intercepts? 1 x-intercept. Okay? And if we look at this last one, so this one opens up and its vertex is at, let's see, it makes it 1 unit sooner, so that would be at -1, and it moves it up 1. So we're right here, and if we were to graph and label a couple of points, those would probably be pretty easy ones to get. How many x-intercepts? No x-intercepts, okay? Because it starts off above the x-axis and then it continues to go up, so it never touches the x-axis. Okay, now, another way to describe where we've got x-intercepts, or that an x-intercept is where it crosses the x-axis, would be where the function equals what? Where the function value is 0. In other words, remember, f of x is the same as y. If the y coordinate is 0, it's on the x-axis. Okay? All right. And then a couple other questions here. It says, how could we rewrite each of these statements using an inequality? So how could we say D is positive by stating an inequality? Yeah, D is greater than 0. Okay? Some people don't like inequalities very much, but they're pretty simple. They're just kind of saying one thing is bigger than another. So if we say D is positive, that means it's greater than 0. Okay? It's on the right side of the 0. And if D is negative, D would be less than 0. Pretty easy. Okay? So we know the graph of a quadratic is called a parabola. Not parabola, parabola. Okay? And we know that solving quadratics, know that we can solve by quadratics by taking what type of roots? Okay, so we learned how to solve them. If there happen to be a perfect square, we can take square roots. We can also do this. It's the math F word. What is that? Factor. Okay, and factor actually works out pretty nice. Okay, or we can complete the square. And what was the last technique we learned? Quadratic formula, using the quadratic formula. Okay, by the way, would you do this for me right now? Right here, would you write down the quadratic formula? Don't say anything out loud. Don't be Elaine and sing it or anything like that. Just write the quadratic formula right here. Check with your neighbor. You have to have this memorized. You have to have this memorized for the test. You really need to have it memorized for the assignments that we do. And you're going to use it again in 1050 and 1060. I gave a calculus test this morning. They used the quadratic formula to solve one of the problems on that exam. So it's negative b, or you can say opposite b, plus or minus a big square root minus, b squared underneath here, minus 4ac all over 2a. Where are the most common mistakes? Where do they happen on the quadratic formula? Minus 4ac part, and sometimes people forget to change the sign. Okay, those are the two places where people make mistakes. So if we were going to solve a quadratic like this, if we were going to solve when that equals 0, really what we're doing is we're seeing where this function equals 0. We're seeing where its x-intercepts are. Okay? Now, as we saw up above here, there are actually three ways that a quadratic, a parabola, can cross the x-axis. Okay? It can cross it once, like we had right here. Okay? In that case, we'd only have one place where it equals 0, which would be negative 3 in this particular case. We call that a repeated solution, or a double root, or a double zero, or different things like that. Okay? The graph can cross the x-axis twice, like we had right here. It crosses once right here, and then once right there. That looks like 0, but it's not. Looks like it crosses through the origin, but it doesn't. Okay? And then in other cases, the graph doesn't cross the x-axis at all. In this case, we get what we call two imaginary solutions. So that's one repeated solution. These are two distinct zeros, two distinct x-intercepts, and this one doesn't have any x-intercepts. The solutions to that quadratic would actually have imaginary numbers in them. Okay? So we're going to solve each one of these using the quadratic formula. Now you'll notice, if I solve this one here, let's see, opposite b, so that's going to be 8, plus or minus b squared, so that's going to be 64, minus 4 times a times c. So that's going to be a 2, and that's going to be a negative 1. And then again, the part that I said be really careful with, 64, am I going to be adding or subtracting here? I'm going to be adding, because I've got a negative times a negative, so I'm going to add, what am I adding? 8? Okay, and then remember, that's all over 2a, so that's all over 4. So I end up with 8 plus or minus square root of 72 over 4. Let's see, this is 6 times 6 times 2. So this is 8 plus or minus 6 radical 2 over 4. We doing okay? Am I going too fast? You'll notice that everything here has a 2 in it, so I'm going to factor out a 2. I'm left with a 4 plus or minus 3 radical 2 over 4. And well, I'm not done canceling yet, right? Now I'm going to cancel those. There's a 2 left, so it's 4 plus or minus radical, 3 radical 2 all over 2. Is that okay? Okay, now I'm going to write this as two separate pieces, just to kind of prove the point. One of them is 4 plus 3 radical 2. Each one of those pieces is over 2. So this one is 2 plus 3/2 radical 2. There's one answer. And what's the only difference when I write this as another separate piece? So that's going to be 2 minus 3 over 2 radical 2. There are the two separate pieces. Okay? So this one would cross the x-axis in two places. It would have two x-intercepts. Any questions there? Okay, let's take a look at the next one. Let's see, these are a little bit bigger numbers, but let's take a good look at this. This is going to be opposite of b, so that's going to be 12, plus or minus, that's going to be 144, minus 4 times a times c, so that's going to be a 9 times a 4, all over 2 times a, so that's an 18. So fairly big numbers, but again, let's make sure we get this underneath here correct. 144, add or subtract? Subtract. What's 4 times 9? 36 times 4? 144. Well, this is pretty cool. Look what we've got here. That means I have 12 plus or minus the square root of 0 over 18. Well, 0 is just 0. Whether you add it or subtract it doesn't make any difference. I've got 12 over 18, so I've got 2/3. Only one answer. What does that mean about this graph? How many places does it cross the x-axis in?
Once.
Just once. Okay, this would be called a double solution or a double zero. Okay, a repeated solution, whatever you want. It only has one x-intercept. Okay, and then let's take a look at the next one. opposite of b, plus or minus b squared, so that's going to be a 4, minus 4 times a times c. So a is a 1, c is a 2, all over 2. And then again, I'm careful right here, 4 plus or minus? Minus how much? 8. So here's what I've got. Negative 2 plus or minus, this would be the square root of negative 4 over 2. Well, let's see, I can simplify that. That's going to be negative 2 plus or minus. What happens when I take the negative out of the square root? I've got an I, then I've got a square root of 4, which is 2. So this is going to be 2i over 2. So the easiest way to write this one would be, notice they all have a 2 in them, negative 1 plus or minus I. So I actually have two imaginary solutions. Negative 1 plus I is one of them, and negative 1 minus I is another one. Remember, we called those conjugates. Okay, are there any questions? Yeah.
So if we're trying to find the x-intercept, how do we graph the negative 1 plus I?
The imaginary ones?
Yeah.
It doesn't cross at all. It would be this case right here. Okay, it would either, everybody listening? Okay, this is the case where it crosses at 2 places, two real number places on the x-axis. Here it only crosses once. Here it doesn't cross at all. So it either has a vertex above the x-axis and opens up, or it's got a vertex below the x-axis and opens down. So the graph never crosses the x-axis. That's what happens when we've got imaginary solutions. Is that all right? Okay, so I want you to take a look at something. In each one of these, when I got done simplifying, or when I was close to done simplifying, you'll notice that I had a 72 here, and I had two different solutions. You'll notice that right here I had a 0, and I only had one solution, and you'll notice over here I had a negative 4 underneath the square root, and I had two imaginary solutions. So the key to figuring out whether or not we've got two solutions, one solution, or no solutions, okay, is by looking at what's underneath the radical. That's really the determining factor. It really didn't matter what negative b was or what 2a was. That didn't really make a big difference. It was underneath the square root that made the big difference. And what's underneath the square root is b squared minus 4ac. And because that number right there, or that expression, allows us to discriminate between the types of solutions we have and how many there are, we call that the discriminant, okay? Because it allows us to discriminate between the number and the type of solutions, okay? So b squared minus 4ac, really important that you get it right. Okay, it's called the discriminant again because it determines the number and the type of solutions we have. Now let's take a look at this chart right here. Okay, this actually is this whole section in a nutshell. If the discriminant is greater than 0, then we get two solutions. If the discriminant is equal to 0, then we get one real solution. And if it's less than 0, then we get two imaginary solutions. So this is just a fancy way of saying the discriminant is, if it's greater than 0, what does that mean? Positive. If it's positive, then we get two real solutions. If it's equal to 0, we only get one real solution. And if it's less than 0, or in other words, negative, then we get two imaginary solutions. Okay? That's really what it comes down to. It was positive here, we got two different solutions. It was 0 here, we only got one solution. It was negative here, so we got two imaginary solutions. Okay? And that's pretty much what we need to worry about. Now, there is one other thing that we ought to be aware of, because occasionally this will happen. If the discriminant turns out to be one of these numbers, what do we call those numbers? Perfect squares. That means that what's underneath the radical will be a perfect square. So when we take the square root of it, we get a nice number. We get an integer. Okay? So what's going to happen there is the number on the top is going to be an integer. A number on the bottom is going to be an integer. So we end up with a rational 0. Okay? In other words, they are rational. Okay? In other words, they're fractions. Okay? If it's something other than that, if it's not a 36 but a 37, if it's not a 25 but a 24, if it's not a 9 but it's a 7, then we get irrational roots, okay, or irrational solutions, okay? Like this one right here. See how it had a radical 2? That's not a perfect square, okay? Now, a couple things about this. When dealing with polynomials, we might use the words, and I've used these already, x-intercept, solution, 0, or root. Those are used almost interchangeably. So occasionally I'll slip up and I'll use a word that we use in 1050, okay? A 0 or a root or something like that. That's all we're talking about. Okay? Now, this is your homework assignment from the textbook. So you need to do those problems there, omit multiples of 3. So that means you leave out 9 and 12 and 15 and so forth. Okay? Do those problems, omit multiples of 3. Do 53 and 54. And then I'd like you to log on and do the Math Excel quiz. Just the quiz, not the homework. Everybody clear on that? So book work and Math Excel quiz. Yeah.
Is the homework even going to be an option? Like, will it have it on Math?
Oh yeah, it'll be an option, and you could use that if you need. If you get stuck on something, you could use that for some helps. Does that work? Okay. All right. So flip the page over, please. Okay. Even though this page looks as long as the other pages that we've done, you know, lots of examples and stuff like that. This is how easy this is. You don't have to graph. You don't have to complete the square. You don't have to put it in vertex form or anything like that. All you need to do is take this quadratic and figure out the number and the type of solutions. B squared minus 4AC figures that out for us. That's all we have to compute. So on this one, please take note, take a good look. What's wrong with this? They're trying to trick you. So put it in descending order. Make sure it's set equal to 0. So that's going to be 0x squared minus 7x plus 5 set equal to 0. So that means A is 1, B is negative 7, and C is 5. Let's plug this in and get it right. So this is going to be B squared. That's going to be 49 minus 4 times A times C. We're not going to skip any work here either. So that's going to be a 1 and a 5. All I really need to figure out is this is 29 minus what? Did I? Oh, see, I've got number issues. Okay, 29. Okay, this is the discriminant. Now, if this were a test question, I'd want to see the 29. But from there on, there's really not much work. It's just thinking. Positive, negative, or 0? It's positive. Okay, that's positive, so that tells me something. That tells me that I have 2 real zeros, okay, or we're calling them x-intercept, we'll call them solutions. Okay, 2 real solutions, and I should look at this and think, I mean, it'll usually jump out at you, is this a perfect square? No, so we'd stop right there. What if it was 25? Nope, not one solution, it's positive, so we've got 2. Okay, we'd say it's 2 real, we'd insert the word here, rational. Let's take a look at the next one. Okay, is this written in the correct order? It is. Okay, what's A? A. Thank you very much. I'm listening to Christian too much. Okay, B is 0 and C is 11. So if I do B squared minus 4AC, this is going to be 0 minus 4. Again, can't screw this up. 1 and 11. What is the value of the discriminant? Negative 44. In our minds, we think, hey, that's negative 2 imaginary. That's it. That's all there is to it. You do a couple simple calculations. You think, hey, that's negative. I've got 2 imaginary solutions. Let me ask you this. What if it had been negative 49? Would that do anything for us? There's no such thing as a rational imaginary number. Once it's imaginary, it's just imaginary, okay? I'm sure that'll come up at some point. Okay, so take a look at this. What's good about this? It's in order, and it's set equal to 0, so we can identify A, B, and C. What's not so nice about this? Really big numbers. So we're going to write negative 48 squared minus 4 times A times C. So this is 9 times 64. I'm then going to grab a calculator and I'm going to let it do the work. So let's make sure we type it in correctly. So I'm going to do, it doesn't matter whether I do negative 48 and square that or positive 48 and square that. As long as it's in parentheses, it's going to end up being positive. And then minus 4 times A times C. Did I type it in right? What do we care about? Positive, negative, or 0? The value of the discriminant is 0. So we keep track of that. That means we have 1 real. Well, wait just a second. Is 1 a perfect square? Is 1 a perfect square? Yeah, it is. It's a perfect square of 0. So not only is it real, it's also going to be rational. Okay? Now, we had one earlier that turned out to be 0. Let's come back up here and take a look. Now, rational, remember, means it's a ratio, it's a fraction. Let's come up here. That one right there had a discriminant that was 0. And look at the solution. It was just the fraction 2/3. Got it? Okay, you do the next one. Check with your neighbor, please. It's in descending order. That's good. When you get your answer, again, check with your neighbor. If I square b, I get 1 minus 4 times a times c. That's a 10 and a negative 2. So I'm really going to be adding 80. So the value of the discriminant is 81. That's the value of the discriminant. We know it's positive and a perfect square. So what does that mean? 2 real rational solutions. Okay? So that means it crosses the x-axis in 2 nice places, or reasonably nice. All right, fractions aren't your favorite, but that's the way it is. Get used to it. Okay, any questions? Okay, now it gets kind of interesting and a little bit easier. Okay? The easiest way to find solutions is if the quadratic is already factored, or if it's easily factorable. Okay? So we talked about this last time. First on our list is we get everything on one side, set it equal to 0. If it's already got a perfect square, you can just take a square root. Okay? It's not a perfect square, try and factor it. If it doesn't factor or solve using the square root property easily, then we use the quadratic formula. But on this one right here, multiply to be 4, combine to be 5, positive 1 and positive 4. Solution that comes from here, negative 1, and from here, negative 4. There are the answers. And you could confirm that using the quadratic formula. It'll give you the same thing, but this is just quicker. So let's take a look at this. I think we talked about this before. If this is my factor, what's the quick way to figure out what the solution is that comes from that? Opposite of the constant, so that's going to be negative 3, divide by the coefficient. Now that only works if this is a linear term, a linear factor. Okay? So this is going to be negative 3/2. There's one answer. What's the answer that comes from here? Opposite of this, that's going to be positive 1, divide by the coefficient. So I've got negative 2/3, or negative 3/2 and 1/4. On this one right here, it's easy, right? Negative 7, that's it. Now, it doesn't matter that this is x plus 7 times x plus 7 if we were to write it in what we call expanded form. Doesn't make any difference. There's a negative 7 from here. Once I know negative 7 is an answer, is there a point to repeating it? No, okay? That's the solution. Now, when you get into 1050, the fact that this is squared is going to mean something, okay? And on this one right here, this is positive 6 over 5. What about this one? For some reason, people have trouble with this. 0, okay? So this has 2 solutions, 0 and 6/5. Any questions? Again, keeping in mind that you're going to use these same skills when you get to 1050. If you know what an x-intercept is, you can actually make the polynomial, or the quadratic in some cases, that had that for an x-intercept. So this says write a quadratic in the form ax squared plus bx plus c equals 0 that has these as solutions. So let's think about this for just a minute. Take a look up here, and then take a look at this. How are these problems related to these problems? They're the opposite, okay? It's the opposite process. Instead of starting out with the polynomial, factoring it and coming up with the zeros, they're giving us the zeros or the solutions, and we have to come up with the original polynomial. So if 2 is a 0 or a root or an x-intercept or a solution or whatever you want to call it, what factor must it have come from? X minus 2, right? Change the sign. The number underneath there must have been a 1. Slide that 1 out in front. Everybody get that? Change the sign here. Slide that 1 out in front. Okay? So it would be like 1x minus 2. Does that make sense? Okay. What about this one? X plus 1. Or when they're easy numbers like this, you can just take it and change the sign. 2, negative 2, 1, negative 1, positive 1. Okay? Now, are we done with this problem? We're not, because we have to set this up and say, well, really, this is why these were solutions, because when we multiplied them together, we got 0. Well, now let's multiply these together. I get x squared minus x minus 2 equals 0. That is the polynomial or the quadratic equation that had those as zeros. Okay, let's do this one. What's the factor here? X minus 1. Let's do this one. Let's make this the easy way. Remember, the top comes from this one. It's going to be the opposite of that. Why is there a 2 in the denominator? Because there was a 2x there. Again, set this equal to 0. The hard part is out of the way. We've kind of solved this in a backwards fashion. Now all we need to do is come up with the polynomial. So that's going to be, 2x squared. It's going to end with a positive 1 minus x minus 2x. So that's going to be minus 3x altogether. So if you were to solve this, we did this in chapter 5. We solved equations like this. Okay? We've got a quadratic. The only zero, the only solution, the only x-intercept is negative 3. What factor must it have come from? X plus 3, and that would have had to have been quantity squared. So this would be x squared plus 6x. See how nice it is that you know the pattern for a perfect trinomial square? And let's take a look at the very end there. It says, find a degree 3 polynomial that looks like that. So notice all we do is we add one more term. So we've got an x cubed, an x squared, an x, and then a plain old constant term that has these as solutions. So if 1 is a solution, what's the factor that it came from? X minus 1. If negative 2 is a solution, it must have come from a factor of x plus 2. And if 3 is a solution, x minus 3. Set that equal to 0. Am I done? No, but it's pretty easy from here on out. I just multiply those together. So that would be x squared plus x minus 2 for the first two. And then I need to multiply that by x minus 3. You can finish it from there, right? X cubed, x squared, minus 2x, minus 3x squared, minus 3x plus 6. And then I just collect the like terms. So my final answer is, let's see, I've got an x cubed term. I'm done with that. How many x squareds do I have? Negative 2x squared. Done with those guys. How many plain old x's? Negative 5 of them. And I've got that constant sitting out on the end, just that plus 6. There we go. That's actually a problem from 1050. If you can do that, you already know how to do part of a section in 1050. Okay, are there any questions? Okay. All right. That's it. Go ahead and get busy on the book work. How many of you brought your books today? Excellent. Thank you very much. I will pull up